But the graphing one, yes. Okay. So, not exactly. I think we left off right around here. Evidence of chemical change. Is this ahead of where we left off or behind? So we talked. Did we talk about precipitates last week? Okay. So precipitates, and then common misconception that boiling water makes H2O or O2 and H2. It's not. It's just those intermolecular forces that are being broken. Spectator ions, remember, should not be included in your balanced equation. So your net ionic equation is going to show what ions are actually taking place in the precipitation reaction. You'll also need to know that if it's a redox reaction and they ask you for a net equation, then you would also show anything that's being oxidized or reduced. All right, mole to mole reactions, mole ratios here. I usually show you guys those with the BCA tables. Talked about conservation of mass, so make sure that if they ask you to draw a particulate diagram, or if you're looking at comparing particulate diagrams, that you end up with the same amount of stuff on each side. So here we've got 2, 4, 6, 8, 10, 12. Over here, we should have 12 of those lighter colored circles. Here we've got 4, and over here we do. So make sure that when you're drawing these, that you have that taken care of. Okay, so here we have a particulate diagram, and the answer for this one was D. Does anybody have any issues or questions with that? Okay, that one was pretty easy. Here, you had to find the mass of copper. Find the mass of the copper, heat in the oxygen to a constant new mass, subtract the mass of the oxygen that was lost, and then combine with the copper, and then compare the moles of oxygen to the moles of copper. So this was a decomposition reaction down here. For decomposition reactions, again, this should be an arrow here. It didn't quite show up right when it switched this over to a new version of PowerPoint. Find the mass of the calcium carbonate in the sealed container. Evacuate the remaining gases. Heat the container and take the pressure readings. And that is going to be the pressure then that's exerted by the CO2. Because this is a solid and this is a solid, this is the only thing that's going to contribute to that pressure. So then you calculate the moles of carbon dioxide that are present, and then that you can use your molar relationships to figure out other data. Here you had heating to constant mass. That's another term that they really enjoy you using properly. So heating to constant mass, you're going to determine, so the formula down here is SnO2. Anybody not get that formula? You did well on this one. All right, making predictions. Did you have to write equations for these, or did you have to write any equations for any of these? Yes? Yeah. Isabella says yes. Okay. Remember, these two boxes are actually an arrow. It just didn't transfer well. So there's your first one. Any questions on that? So this was a decomposition reaction. Here, what evidence would you see? You could see a color change, and you could also see gas coming off. Then you had a percent yield. You should have ended up with 89.9 or 80% is probably what most of you ended up with. And then how could you improve it? You could reheat the solid to see if there's any more mass lost, or you could make sure that the copper carbonate was solid. Or pure, I mean. Okay, questions? Ready to move on? Okay. Synthesis reactions, then we're combining two different things together. So you're going to heat mixture. You have a mixture. You're going to heat it until none of the aluminum's left. Then you add in sulfuric acid to precipitate out, and then you recrystallize that alum in an ice bath. Then you filter and collect those, and you're left with the pure substance. Gravimetric analysis, then, that is just a fancy term for using mass. Okay, they try to make this look really complicated by using some big word. They're trying to get you to use mass. Okay. Remember, you always have to be in moles here to be able to do stoic. Only moles in the holes. Okay. Filter and weigh. All right. So if we had contamination in the solid, you're going to end up with a mass that's too large. If you did not allow that precipitation reaction to continue long enough, then you're going to lose some of those ions as a filtrate and your mass is going to be too small. If you don't evaporate off all of the water in there, then your mass is going to be too big. Then we had double replacement reactions. So here, typically what you're going to do is you're going to have a situation where you're going to have some sort of two aqueous solutions are brought together, and those two of the ions in that aqueous solution are going to end up giving you a solid. All right, so you had to identify your limiting reactant here, which should have been water. You had to say what the maximum yield was, and then how much excess reactant was left. How did you do on those? Anybody need me to run through the math on that?
Yeah, theoretical yield, please.
Okay, so theoretical yield, that I taught you guys using a BCA table, I'm guessing. Yeah, so they have given you on here 15 grams and 10 grams of water. So I've got to take this and I need to turn it into moles. I have to turn this into moles. So 10 divided by 18, 15 divided by 27 is 0.556. And then 10 divided by 18 is, oh, that's the same, 0.556. Now, to go up, remember we go up into the cloud, we divide by this. So I'm going to divide this one by 1. So that's 0.556. This one I'm going to divide by 6. So that's going to end up being 0.0926. Get rid of all but the smallest cloud. And then you're going to use this to figure out your values. So water is our limiting. They're asking us theoretical yield of this. So I'm going to bring this over. I'm going to multiply this by 3. So that ends up being 0.278. Okay. So that gives me my moles. That is moles. And now I need to multiply that by the molar mass of this, which is 34.1. So that ends up being this value.
Okay.
I just take a different route than they do. They use dimensional analysis. I use this. But see what I did up here in these steps took them all of these steps to make that happen.
Yeah.
That's why the BCA tables are much faster. So yeah, you could set this up using dimensional analysis. And what you do when you do that is you see which one of these, you're going to need less. And by then, you've done so much of this stuff. It's a time suck is what it is.
What do you get? 0.0926?
Here, I took the 0.556 and I divided by 6.
Okay.
So then that becomes what I'm going to multiply through for all these other things. But that's the beauty of the BCA table. Good? Questions? Other questions? Anything else on there that you didn't get right that you got questions on? All right, we're going to keep moving then. We've got 15 grams of aluminum sulfide and water reacting. Oh, that was the same equation. So this is the BCA table method of doing it, and you come up with the same answers. Good. This is my preferred method. All right, strong acid strong base gives you salt and water. Where's your equivalence point going to be at this, in this graph? Or if you were to graph the titration? 7. pH is 7, okay? Strong acid, strong base, equivalence point is always 7. All right, so here they are figuring out, they've got 25 mils of HCl. They're titrating that with 14 mils of calcium hydroxide. And what is the molar concentration of the HCl? So you're going to take this guy right here. That's his, no. Oh, they gave us values here. Okay, so this is the calcium hydroxide. You would subtract these out, which means that you used 0.0234 liters. You're going to multiply that times 0.15, and that's going to give you the moles that you would have had of your H plus. And then if you divide that by 0.025, that's going to give you your molarity. Okay.
You take the mole H plus from multiplying the molarity by the.
You take the molarity times the volume of that you use. So this, but you started here, so you actually only used that much. You know, if we want to talk about get rid of our initial and our final, this is how much, but then you have to have that in liters. Good. Okay. Multiply that by molarity. That's going to give you your moles of H plus. So 0.15 times 0.0234. That's 0.00351. And then I'm going to divide this by 0.025. And that gives me a 0.14 molar concentration. If the student accidentally overshot the equivalence point, how would this affect the calculation? Well, it would increase the molarity of your H plus by doing that, because what it's going to do is it's going to increase this number. That number will then drive this number up, which then drives this number up. All right, then we had redox. Remember, my preferred acronym is oil rig, but you can go, Leo goes GER if you'd like.
Oil rig. I like oil rig.
Yeah, oil rig is the one that I use. So remember when we're transferring these, you've got to look. If it is a solid here, that's a 0. If it's a diatomic, it's a 0. Here, you've got a +2 and a -2. So this guy, magnesium, has done what? Magnesium has lost electrons, so it was oxidized. And the oxygen gained electrons, so it was reduced. All right, what did you get for your answer here? Hopefully you got C. So C is your answer to this problem. Anybody not get C and we need to go through it? All right, redox titrations then. We actually did this titration in class. We had, so you were able to tell what was titrated. All right, we're on to kinetics now. State of reaction then, rate increases as you go from a solid to a gas because you have more collisions. Temperature, the higher the collisions, the more, or the higher the temperature, the more collisions will occur. Concentration, the more reactants you have, the more things that they've got to bump into. And then the catalyst can also be used to speed up the reaction. You need to make sure that you have these graphs memorized and what they mean. Okay, you can tell what order this is by finding where it stays the same here and it changes here. Here it doubled. This stayed the same. What happened here?
They stay the same.
Stayed the same. So what order reaction is it?
First. Zero.
Zero. Okay.
It's first if it doubles.
Yep. So A doubled, but there was nothing happened to this. So A is going to be 0. Here, when we look at B, if A stays the same, so we got to find a spot where A stayed the same, which is here. B doubled here, this doubled, so that means that it's first order. So overall reaction was first order because that doesn't get brought in.
Is it 0?
A, it's 0 with respect to A, because here, when A doubled, nothing happened to the rate. So with respect to A, it's 0 order. With respect to B, when we doubled B and kept A the same, then it was first order. So the overall reaction order, you would add those together, and 0 plus 1 is 1. So this is the rate law for that. All right, you had different conditions here. All right, did you have this one where you had based on the information above which mechanism is consistent with the rate law? Okay. This is kind of garbled here. Well, I hope it was set up a little bit better on your page. The answer was both are consistent. Did you get that answer?
Yeah.
Okay. Yes, no, I can't hear.
Yes.
Okay. All right, then you had this guy. It says rate law here is found to be rate A squared B. What's the intermediate? So were you able to find the intermediate?
Yeah.
How is E oh, E is the intermediate. I see what they're saying. I was looking for option E down here. Oh. Okay. Good. All right, exothermic versus endothermic. How many steps did this reaction?
What's the answer to the last one?
E as an well, no.
There's only.
Okay. E is the intermediate. Only mechanism 2 is consistent with the rate law. So it looks like B is in boy.
Okay.
All right. So here you have different graphs shown. Okay. How many steps, how many elementary steps are in this reaction?
2.
2. You can tell that from this. Which one is your rate determining step? Step 1 or step 2?
2.
Step 1, it has the highest activation energy. Is this an endothermic or an exothermic reaction? Endothermic. Okay. What type of reaction is this? Exothermic, right? Okay. Label the axes, match the curves with the appropriate description. Which step here is the slow step? Second one. Okay. Endothermic, exothermic? Endo, 1 step. Endothermic, exothermic? Exothermic. Endothermic, exothermic? Endo, how many steps?
2.
Which one's the rate determining? Same here. Endothermic, exothermic? Exo, how many steps? 2. Which one's the rate determining? First. All right, we have a catalyst here. It's going to be lowering activation energy. It can participate by forming intermediates. It can also participate by reducing activation energy. So here is the Haber process for producing ammonia. And that simply takes this, we've got rate determining step here, and then your formation down here. Here's an example of where they've taken an uncatalyzed reaction and brought it into 2 steps and lowered the activation energy by doing that, making it more likely to occur. All right, kinetics and collision theory, reactions that have a delayed physical change due to mechanism, which only has a later step show color change. Concentration versus time can be gathered in these labs. It's important that there is a relatively low amount of sulfur disulfur trioxide, so that the I3 will accumulate and show the color change. All right, so which of the following would increase the rate of reaction? You should have, oops, this is not gonna discard. The answer is D. Anybody not get D on that one? D is good. Everybody's good with that?
Yeah.
Questions about it? All right. Thermochem then, when we're looking at thermochem, you need to make sure that you understand certain vocabulary terms: universe, system, surroundings, endothermic, exothermic. So universe means the system and the surroundings. The system is the species that you're studying. And then the surroundings are typically what you study in order to gather information about this. So like your thermometer is going to be part of your surroundings. All right, kinetic energy then is going to be transferred between particles of varying temperature. Heat flows from an area of hotter to cooler. Energy is conserved in those reactions. And we can use those to be able to expand or compress pistons, for example. Endothermic, exothermic, we've already talked about these. Make sure that you realize that the energy that's absorbed here is your delta H. This is from where the reactants start to the top. That is your activation energy. Maxwell-Boltzmann distribution, you will see at least one of those on your test. I would almost put money on it. Temperature is a measure of the average kinetic energy of a subsample of substance. Remember that if you have something at a lower temperature, you've got less average kinetic energy across the board. All right, this is another graph. You guys saw one of these when you were working with your graphing activity. Bond energy is always endothermic, that you have to have energy to break those bonds. If the energy to break the bonds is greater than the energy required to bring them back together, then you have an endothermic reaction. Heating and cooling curves, I wouldn't be surprised if you weren't showing one of those on there. When we look at things being dissolved, the particles have to separate. That separation requires energy, and then energy is given off when it comes back together. Energy when mixing then, when we're mixing these two things together, oftentimes things feel warm. So you actually, the system, the surroundings will gain energy, the system loses them. Calorimetry then, we've talked about that and how to do those calculations. All right, questions here. Is this your next question in your packet?
Yes.
Okay. Let's see what you got the answer. Did you get B to this one?
Yes.
Everybody doing good on this?
Mm-hmm.
All right. So formulas there. Equilibrium. Yay.
Yay.
So chemical equilibrium, we're starting out here. We're manipulating K and Q. I like to put K in front of Q because then that indicates to you which way the reaction is going to run. So if you have a reaction such as like we're dissolving NaCl from a solid to aqueous, okay, if I think of this in terms of K versus Q, my K value for this is always greater than 1 because this is almost always soluble. So we're just going to call it 1 now. if I get a situation where I calculate Q, and remember, these are the only things that we're going to use for Q here. If I get a situation where I calculate the concentration of these, I multiply it together, and that's like 1.25, then my Q would be greater than my K, and that would make the reaction run back this direction. So if you list K versus Q and you calculate each of one of those, or you're given one of them, that will tell you which way the reaction is going to run. If we end up with a situation where Q equals 0.25, then this is going to be the opposite sign, and that reaction is going to run this direction. So that's how I put it. I put it in alphabetical order. All right, kinetics and equilibrium then. You can examine the rate at which the reactions proceed. Your rate laws then are used to describe how the reactant concentration affects the reaction rate, and you end up using rate constants like K and a rate law. They're determined experimentally. All right, we talked about K versus Q. They listed Q versus K here. I don't like that. All right, calculating K, you're going to write your equilibrium expression. You're going to do your partial pressures or concentrations, depending on what you're given. And then you're going to sub that into the equilibrium expression and solve. So here, you should have ended up with this for your answer. Did anybody not get that? You want to go through it? Good? All right. Here's K. You were supposed to calculate that. Were you able to get that correct answer for K? 6.5 times 10 to the 2. Everybody good? No explanation necessary? This is the time to ask questions. All right. You had the next one, given the following reaction. Is that your next one on your sheet?
Yeah.
Okay. There's your partial pressures. Anybody need me to go through those?
Me. I do not know how to do that. I know what partial pressures are. I do not know. It's the ice table. Oh, okay. I could just read it. Well, I need to show you.
This is 0.5. Initially present, they didn't have any of this. So ICE, this is going to lose X, and this is going to gain X. So 0.5 minus X, and this will be X, but this is actually 2X. Sorry. 2X. There we go. All right. And then we have our K value. So our K was given. That's going to equal our product squared. So that's going to be 4X squared over 0.5. So I'm going to ignore that X. I can ignore that, but I have to document it. Okay. So then 4, let me see, no, point. K was given here, so that is 1.13 times 10 to the minus 4. I'm going to multiply that by 0.5. That's going to equal 4X squared. I'm going to divide both sides by 4 then. And then I'm going to take the square root of that value to get X. So that is 1.13 times 10 to the negative 4 times 0.5 divided by 4. And then I'm going to take the square root of that. That ends up being 0.0037. Okay. They wanted to know the partial pressures. Okay. So that's going to be, I have to take this value and multiply it by 2, which gives me this. And then I have to take this value and subtract it from 0.5, which gives me that. All right. Moving on. Magnitude of K. If you're looking at K and it's very small, that means that it's going to favor the reactants. The products, you're going to have very few. A very large K then favors the products. We talked about Le Chatelier and how that affects things, different shifts based on that. They're giving you an example here where they were adding different things together. Then you could talk about different shifts and the effect on K and Q. And finally, we come to our answer, and you should have had D. Questions on D? All right. Then you had another one. So you should have had C on this one. Questions on that guy?
What? What's it say?
So it comes down initially, if you look at these, they want to know which one is which has the smallest KSP value, right? So here, this is how soluble they are. So these two are automatically out because they have a pretty good solubility. Now you're running a race between these two. So here, if we look at these, we're looking between these two right now. So you quickly establish that since this would be raised to the 4th and this raised to the 3rd, you're going to end up with 10 to the negative 27.
Why
So
is it raised to 10?
My logic's there. I'm just giving
Fine, 43.
Is it supposed to be a person that's a heart?
Yeah, I don't know what you were doing. Yeah. I didn't want to say anything though. There's only 5 people on your team.
I don't know why it's the 4th. Oh, I do. Okay. So, wow. Sorry, guys. When you're doing this, this is a CROH. This would be a +3. This is a -1. But you have 3 of these, and you've got 1 of these. That's a total of 4. So you're going to be taking this and raising it to the 4th power. Because it would be KSP equals X times 3X cubed here. That makes sense now. So that's where they're getting these mathematical amounts here.
Would 9x to the 4th?
I like that my drawing. I felt so
27.
So 9x4, yeah. But if you drop, well, this would be 27 though, actually, because 3's cubed. But if you just drop out and just start looking at the x's total, because that's really what this comes down to. You don't care so much about this forward part. you're able to quickly see that this is going to be much greater here, because this is 10 to the negative 8th raised to the 4th versus 10 to the negative 9th raised to the 3rd. So this is going to come out much less soluble than that when you're trying to figure out your KSP values. All right, common ion effect. When you got an ion in common, it's going to reduce the amount that is soluble. Then you had qualitative analysis where you're looking at different colors. So different anions and the like. Then you've got acids and bases. We've talked about those very recently. That's why I'm speeding through some of this later stuff, because we've been through that more recently. So we talked about different strengths of acids and how this guy here is going to be a stronger acid than these because it's got more oxygen holding that hydrogen in place. Bronsted-Lowry, remember you want to pick the two things that are paired up together that look alike or look very similar, and then you're going to find the one with more hydrogen. That's going to be your acid out of that pairing. Weak or strong acid. Weak acids do not disassociate much. Strong acids disassociate almost completely. KW, remember, is for water at 298 Kelvin. So when you're at 298 Kelvin, 7 works for your pH for both things at that point. But if you change that, then you're going to have to change the pH where that equilibrium happens. Then you've got to look and see, is it strong? Is it weak? Is it a salt? Is it a buffer? How does it react in water? And then you had here a question. You should have ended up with C as your answer. Any questions on that?
Sorry.
Then you had titrations that you were looking at. This is a titration of what? How many? This is a diprotic acid here. Okay. You started out here. You had one plateau. You got 2 plateaus. So that is a diprotic acid. Remember our equivalency point. If it's at 7, we titrated a strong acid, strong base.
Please.
Here they're asking you which one, with this titration, which one you ended up with representing the pH of the solution at the equivalence point. You should have had D there. This is known as what? Half equivalence. At half equivalence, what equals what?
pK equals pH.
pKa equals pH. So that will give you, if you know the pH, that'll give you your pKa, and from the pKa, you can go 10 to the negative pKa and get the Ka. Okay? And then you can use that to be able to set up your equations. So that is a very important point on that graph. All right, next one you should have ended up with B as your answer. Questions on that?
I remember doing this. Yeah, do the titration.
This is another one that they didn't.
Oh, you didn't like that? I don't know how to do that.
All right, you should have gotten E for this one.
We have that one?
Do you or not?
Yeah, it's not good to do. It doesn't have
Oh, I'm chilly in this room right
I think
now.
the graph was from the previous problem. The graph's the same as the previous one. So this is E. So they asked, the hydrochloric being added. So yeah, E would be that. All right. Then on to thermochem. We're going to embrace the chaos here. We've talked, don't say like dissolves like. They don't like that. Naughty, naughty. Memorize this thing. Get this thing memorized. Lots of ways to calculate G. Pratt-Link. All right, then you had this guy. You should have ended up with B for your answer here. Yay or nay? Okay. Then you had half cell reactions. Here you should have ended up with C.
Whoa.
It ran out.
No, we have that one. Oh, I thought it was 53. Never mind. I have it.
What order, Lola?
Oh, wait, never mind. I thought I did. I have like everything, but I don't have that question. I have the self-function.
Coupling reactions, you just add them together. Talked about those.
I just remember to back to you.
Okay, so tomorrow, guess what you're going to start?
For test.
Yep,
Tomorrow's our test.
you're going to start it.
Okay.
Oh, wow. I just can't.
Oh, but you can.
Can you send me the slideshow?
Oh, did you like my
Did
computer?
I not? I'm sorry.
I don't see it. Why did you- oh,
Start with
I see it.
MCQ, Mo?
No, we'll start with FRQ.
Open it.